Get started. So my name's David. This is Alon over here. We're representing a very large team of people who work on FireSim at Cal. Sagar couldn't make it today because he's going to a wedding. So this talk is going to be broken into two parts. The first 10 minutes I'm going to be talking about sort of the motivation for why we built this thing and some of the underpinnings of the technology. And then Alon will be giving sort of 10-minute overview of the cool things you can do with FireSim. Okay, so I'm kind of preaching to the choir here, but you know, NRE is a huge barrier to building chips, and the world needs more custom silicon, in my opinion. And if you look at the source of NRE, unfortunately, there's sort of a myriad of different sources, and it's sort of a death by 1,000 cuts. And so if we're going to overcome this, we're going to need a large community effort. And so the focus of this talk and the components of NRE that we're attacking relate to how we do full system simulation of an SoC. So specifically, I'm going to be talking about how FireSim enables better full system simulation for doing pre-silicon verification, validation, and software development, which represent the largest components of NRE in a new chip start. So ideally, if we were building a magical full system simulator, it would be as fast as silicon and as detailed as silicon, so that we could boot, you know, a real operating system and run our desired application on a very detailed model of the machine, right? So we could do pre-silicon validation, but also pre-silicon verification. It would have all the benefits of a conventional software-based simulator, so great visibility. It would, you know, recompile instantly. It'd be productive to debug, right? And of course, it'd be low cost. In reality, the adage is you can only pick some subset of this, 2, maybe 2.5 at best. But our thesis is if you wanted to do better, currently FPGAs are the only viable basis technology, because FPGAs can support running cycle-accurate simulations at tens to hundreds of megahertz. And because they're a commodity part, they're relatively low cost. You don't have to go build an ASIC for this. So with FireSim, what we're trying to do is build FPGA-accelerated simulators that have a lot of features that resemble those that you would get with a conventional software-based RTL simulator. And we're going to do all this with an open source tool. So FireSim really leans on and leverages a number of technology changes over the past few years. Firstly, we use FPGAs in the cloud. They're large and ideal for ASIC emulation. And so we can also ask for an elastic number of these, which is great if you're trying to batch out experiments. FireSim is built with Chisel. We lean heavily on Chisel to design all of the sort of simulation infrastructure that we use to support a simulation. And then we use Fertile to take the design under simulation and transform it into something that's host decoupled using compiler transformations. And I'll get to that in a bit. Of course, we need something to simulate. And in this regard, we use RocketChip. And of course, RocketChip implements the RISC-V ISA. And so if you build an SoC with RocketChip, you can pretty much simulate it in FireSim in very little time. And so the upshot of all this is that you can build a simulator that's cycle exact, deterministic, and can boot, you know, a real operating system and run something like spec at order 100 megahertz, which is pretty good. So at a high level, what is FireSim? It's really a tool that builds deterministic FPGA-accelerated simulators for doing pre-silicon validation and verification. It consumes as input your RTL design, which is specified in Fertile, so you can use Chisel and emit Fertile, or you can use the backend in Yosis, and so this is one means to get Verilog into FireSim. It's in progress still, but we'll keep you apprised. The other important component is you need some set of hardware and software I/O models that you're going to use to close the simulated world. And that's how you produce a closed system. And FireSim provides software models for UART and Ethernet, as well as an FPGA-hosted model for DRAM. And finally, you have some description of the thing you want to run, the software you want to run on your simulators, and that's the workload description. As output, FireSim is going to build a cycle-exact simulator of your design and the models around it. And so that consists of building a bit stream that goes into the FPGA and a binary which runs on a host CPU because these things are co-simulators. Secondly, FireSim provides a lot of tooling for batching out simulations into the cloud. And so that's how we can do productive design space explorations, and also batch out things like spec over multiple FPGAs. Okay. So if I want you to come away with something today, there are really 3 distinguishing features of FireSim. Firstly, and most importantly, it's not an FPGA prototype. And that is to say, we're not taking a rocket ship and we're synthesizing it directly to an FPGA. Instead, what we're doing is building something that resembles something more like a commercial co-simulation platform, like a Synopsys HAPS, for instance, where you have models that live in software and they're talking to models that live in hardware, and the things are executed deterministically. We use cloud FPGAs. I already went over this a little bit. They're inexpensive for researchers because AWS has been pretty supportive in giving credit. But they're also very large. It's ideal for doing ASIC emulation. You would have to spend around $4,000 to buy a dev board with an equivalent part. And using cloud FPGAs is great if you're collaborating with other researchers at other schools. You can just spin up a simulation regardless of where you are and produce the same result. And of course, it's open source. So unlike those commercial co-simulation platforms, all the stuff we provide is free, assuming you can get credit, of course. But the DRAM models, all these I/O models are things you typically license from a vendor. We provide them for free. So why is FPGA prototyping insufficient? So we're going to run through a real simple example that motivates why you need something like FireSim in some cases. So if you tape out a chip in some process technology and say it closes timing at 1 gigahertz, it's going to talk to some real DRAM memory system and maybe see on average about 100 nanoseconds of latency. If you synthesize that design onto an FPGA, obviously it's going to close timing at some lower frequency. But in order to model DRAM, you're probably going to have to use the DRAM attached to that FPGA. And that's a real memory system, right? So that has the same approximate latency, if you would permit me to make that assumption. And so as a result, the SoC is going to see a memory system that's artificially fast, right? And so this is symptomatic of a larger problem with prototypes, and that is that they essentially couple time in the simulated system to wall clock time, which is not something that's true of software RTL simulators. It's just something you take for granted in that case. And so as a result, the latencies in the FPGA host platform are directly exposed to the simulated world. And there are 3 implications of this. Firstly, if you're using FPGA resources like DRAM to model parts of your ASIC, they might not be accurate. And that was the previous slide. Simulations aren't natively deterministic, which makes it hard to reproduce bugs in some cases. And of course, if you build a prototype on 2 different FPGAs, their simulation results aren't going to be the same necessarily. So key to understanding how FireSim works is understanding that there's a separation between target and host. Target being the machine under simulation, and the host being the machine actually executing the simulation. And going back to the previous example, it was that ASIC, and really, we want to think of the target as this closed simulation world so that we know a priori how it should execute, and so that we can execute it deterministically on different hosts. So one such host could be an FPGA. It has some fabric and some DRAM. Alternatively, it could be a multiprocessor, right? These are just different hosts. FireSim generates FPGA hosted simulators. And so one analogy, and again, I'm kind of stretching it here, but you would use Verilator to build a RTL simulator that's targeted for a multiprocessor. FireSim is useful for building simulators that are hosted on FPGAs because it's not trivial to make these things execute deterministically in a host decoupled fashion. Right, so this process of taking your RTL design and building a deterministic simulator that runs on an FPGA is what we refer to as host decoupling. So again, take the example from before. There's a series of steps. The first thing is we break the target into a graph of models that are latency insensitive. So this is basically pulled out of Luca Carloni's paper. You take the RTL, you decouple it with a decoupling transformer in Fertile. Then you need to generate I/O models. In this case, we generate a custom DRAM model that's sort of a timing model that lives in Fabric and uses DRAM as a sort of functional backing store. And then finally, we stitch this all together. And so from the perspective of FireSim, the host is this abstract execution environment. There's some Fabric and there's some DRAM. The final step of FireSim involves basically allocating these resources to the various models of the system. So if a DRAM model needs some DRAM, we allocate 4 gigs of DRAM to that DRAM model. And then finally, we implement the rest of the simulator. And the result is you get something that can tolerate latency to host DRAM and executes deterministically and provides that desired realistic DRAM latency. So I'm running a bit over time, but the benefits of doing this hosted coupling are widespread. So firstly, like I said, our simulations are deterministic. That makes it convenient to reproduce bugs and hunt them down. And you can host simulations on different FPGAs and get the exact same result. And this enables support for a bunch of cool features that Alon will talk about. Firstly, software co-simulation. You can put arbitrary models in software. You're going to pay a transport latency cost, so you need to keep that in mind. We can simulate very large machines that are distributed over very large hosts. And so that's what we did in our ISCA paper, in which we simulated about 1,000 quad-core nodes on AWS. And then finally, because we can halt simulator arbitrarily, we can inject non-invasive debugging and instrumentation. So we can measure things about the core and provide features that look a lot like features you would get in an RTL simulator, all without changing the behavior of the simulated system. And now I'm going to pass it over to Alon.
Hi. So I'm going to talk a little bit about what cool things people have done with FireSim, either in our group or outside our group. And the main three types of things that we usually tend to do are evaluate our designs, debug our designs, and try to scale out our designs in FireSim. So let's start with evaluating our designs. Let's say you wrote a new core. You want to compare it to some of the commercial cores out there. You will usually want to run some benchmark suit, let's say spec. Now you can run spec with a small input size and run it on your RTL simulator, and that's great. But if you want to compare it to the real result with reference inputs, that will take a very long time on a standard RTL simulator. However, on FireSim, you can run the entire spec in 2017 with reference inputs, which is like the full big suit on Rocketship, and it takes you less than a day, within a day, because you can parallelize it across multiple FPGAs, and you get it at FPGA speed, which is around 150 megahertz, which is fairly fast. Another thing, if you're more academic or want to explore more things, is kind of full system design space exploration. So we take our accelerators, in this case it was the vector accelerator that was mentioned earlier, Hwacha, and we can run kind of a full system design space exploration. We run Linux, we run OpenMP, a bunch of nice software, high-level software frameworks, that machine learning, cafe, all the rage outside, and we can generate a whole bunch of plots because we can configure the hardware in many different ways. Try multi-core, single-core, different memory systems, different cache sizes, everything that we can do thanks to the parameter system that Rocketship has and the other accelerators that we build. We can do this design space exploration, again, parallelized with a full software system running on Linux with every parallel programming paradigm you would like. This is because we can run at these high speeds and parallelize everything across FPGAs. Another thing, what the Boom folks mentioned earlier, you can explore security using FireSim. Again, if you want to try these attacks and you want to run them on real operating systems in real software environments, then you want these high-speed FPGA simulations. So the Boom people already mentioned their Spectre application and mitigations that they ran using FireSim. And more works that have been done outside of Berkeley and inside Berkeley regard accelerators. So we have this Rock accelerator interface in Rocketship, or you can do MMIO accelerators, and people have integrated stuff like the NVDLA that was mentioned earlier, or other HLS-based prototyping and or systolic array machine learning stuff. All of this can be run on FireSim, and basically you can get performance evaluation in deterministic performance evaluation with a real software framework. And the main point here is that you run your real software stack and you don't need to resort to mini benchmarks or kind of pushing specific inputs to get the results you want. You can run the full system at reasonable speeds fairly quickly. The other thing that we want to do with FireSim is debug and profile our designs, because none of us write perfect RTL, and we try to run it on the simulator, and then it doesn't work. So we kind of added a few debugging features to FireSim, and we're still adding them because every time that we write a design, we run into problems, we need to debug it, so we end up adding a feature. So one of the first features we added, it's called Tracer 5. which basically hooks up to the Rockchip debug port and offloads instruction traces and a whole bunch of other details from the debug port. And the idea here is that this does not perturb the actual simulation. So it might slow down the simulation a little bit, but it doesn't affect your software in any way. You don't need to call an interrupt for your perf thing, or you don't get back pressure if you're an actual trace port. And you can offload this whole trace and analyze it in any standard way you would analyze an instruction trace. And what would this type of thing be useful? So we're working on trying to optimize NIC and network drivers. Other people in our group have been working on kind of machine mode or lower level security stuff in the form of secure enclaves. You could also imagine using this for high-performance computing analysis, like where do you get stuck, how many cycles you're stuck on an instruction. But that's one type of thing. The main point here is that this is out-of-band tracing, so you can dump it all. It did not affect your software, and you can analyze it offline or online, however you want. Sometimes you would like to use waveforms to debug, and that can sometimes be hard in FPGAs, and it can be even harder when you're using Chisel sometimes, because you're using kind of this generator ecosystem and you don't have access to the actual signals. So another feature we added is called Auto ILA, and the idea is that you can annotate signals directly in your Chisel generators, and we will automatically expand those, generate ILAs in Vivado from them, or from whatever other ILA interface we have, wire up all the wires to the top level, hook them up to the simulation infrastructure, and you can use the ILA as if you connected it yourself wire by wire to the signals you wanted. So some use cases that people in our group have used this feature include finding various bugs in Boom deep into Linux boot, or identifying memory system bugs in the Hwacha vector accelerator regarding HMOs. And the idea is that these bugs come in billions or trillions of cycles into simulation. So we really would have wanted to use VCS because you want to have access to all your waveforms and signals. But this would have taken us probably 2 weeks to 3 weeks to run a simulation. And using an ILA is a lot faster in that sense. You get your simulation at 150 megahertz on the FPGA. You do need to select the correct signals that you want to see in the waveform, for those of you who've debugged with FPGAs before, but your design cycle is still a lot faster than that 2-week RTL simulation. Another debugging feature that David mentioned that was presented in Dessert, which was a different project, is synthesizable prints or assertions. So these are techniques that come mostly from the software world. We want to add printf debugging. We want to add assertions to make sure that some of our assumptions in the RTL are correct. But when we run that on the FPGA, these things usually disappear. But FireSim enables features that synthesize these statements and allow us to stop the simulation exactly when the assertion was triggered, send a print statement to the host, and basically get software level debugging features in FPGA speeds. It does slow the simulation down a little bit, but it's still orders of megahertz way faster than standard software simulation. Again, this was used in Boom. As you can see, Boom is a fertile ground for many debugging features. And you can find bugs, trillions of cycles into simulation using assertions and printf. The final kind of big idea that you can use FireSim for is to scale out your designs. So David mentioned this idea of co-simulation with some models being in RTL or in hardware, and some models being software models that you don't need the exact RTL implementation for. And the idea is that we can use these trade-offs between software models and RTLs to get a cycle-accurate simulator, but at high speeds and using all the resources that the cloud allows us. So for example, the original intention of FireSim was we wanted to simulate a data center. Now, we could implement the entire data center in RTL. That would take a long time. But what we do here is analyze what do we want to have in RTL that we need that exact implementation that we can use the parallelism of the FPGA, and what can we have in a high-performance software model that we can run on the host and use this co-simulation feature. So in this case, the actual server implementation, the RTL, the processors, we want to have them in RTL and run them on the FPGA because you have a lot of parallelism there. On the other hand, for the network simulation, you have little parallelism in these switch models. You need to coordinate all these distributed server simulations. So we run them on the CPU of our cloud machine. So we basically have a C++ model for the network, and we have RTL for the actual processor and DRAM models, and we co-simulate those on Amazon Cloud instances to get a data center simulation. So how did we build that type of data center simulation? We started with a quad-core rocket chip with a 16 kilobyte L2 cache. It had a 200 gigabit per second Ethernet NIC, and that it has an L2, and it utilized about a quarter of the FPGA. We wrap that up with the simulation infrastructure that FireSim gives us, with all the peripherals, with the DRAM model, with the network endpoints, put it on the FPGA fabric, and that runs in simulation at about 150 megahertz. 40 megahertz if you connect it to the actual network. But then we're still using only about a quarter of the FPGA, so we can plop 4 of those onto an FPGA. So now we have 4 nodes on a single FPGA. Each of them has a quad-core rocket chip, and that runs at about 15 megahertz, still a lot faster than standard software simulation. And it costs you about $1.65 if you're using on-demand instances in AWS. 50 cents if you're using their spot market. Now we want to scale this out into kind of a rack. So AWS has this 16x large instance that has 8 FPGA boards. So now we have 8 FPGA boards. Each of them has 4 server blades. Each of them has 4 cores. They are connected by a top-of-rack switch model, which is in C++. So this brings us to 32 server blades and all the stats that are written there on the right side. Now, we want to add another level of network. So we take 4 of those or 8 of those and connect them through an aggregation switch. So now we have 8 F16 large AWS instances plus another instance for the aggregation switch. And those represent 256 server blades. And we can tack on another level of those, and we can reach a data center simulation of more than 1,000 nodes for a cost of just a couple $100 per hour, which if you would have bought all these FPGAs for yourself, this would have cost probably millions. Price is reduced by now, but it's still a whole lot of money. And when you want to run only single experiments, you don't want to spend this big CapEx. So to wrap up and give a few update slides, so one of the nice things about FireSim is that we automated a lot of stuff here. It's wrapped up by this nice command line program called FireSim. So you call it FireSim launch, FireSim build, and it's very easy. It's kind of a vagrant model. And everything is very reproducible. So because everything is deterministic and is run on the cloud, you can actually take one of the scripts that is in our repo and reproduce all of our results from the ISCA paper from 1 year ago or 2 years ago. And you can get the same plots, and everything runs exactly the same. Because everything is deterministic, everything is automated, and it's nice. And you can do the same thing for spec and many others. We wrote a lot of documentation. This is a simulator. We want people to use it. And at least I think the documentation is very accessible. And if you are a researcher or working in kind of a smaller environment, AWS provides grants. So you can kind of get these AWS credits, and even the small prices that they do charge kind of go away. Some community updates that we have. So a couple of companies are kind of publicly using FireSim. So Esperanto for that Maxion and Intensivate. We have a bunch of projects with public FireSim support, which means they had these AGFIs generated, and they publicly said that they're using FireSim. So obviously Rocketship and Boom, which we've been using for a while. Hwacha, the Vector Accelerator, Keystone, which is a secure enclave project, and the NVDLA. We've had academic users. We've held tutorials at the Chisel Community Conference and at the RISC-V Summit. Mailing list, a lot of cloners. It was selected as one of the top picks of Architecture Conference, so everything is splendid in FireSim world. We're adding a few nice new features. So obviously, one of the points of FireSim is that you want to run real software and complex software. And since software evolves very fast, you can a lot of times get version mismatches, the compiler version didn't match, etc. So we added a new software manager that kind of integrates between QEMU, Spike, and FireSim, and makes this stuff a lot more easier. You can assign different software jobs to different nodes. It builds them automatically. It's quite nice. You should check it out. We are taking first passes at integrating Verilog designs. So obviously, we know that there is still some chisel skeptics in the world. So there are a couple of approaches to integrating Verilog designs. One of them is just clock gating FAME1 transforms. So that's what the NVDLA project did. And there is another HLS project that is doing. The other approach that we're working on is simulating Verilog designs through the Yosis deferral compiler that was mentioned earlier. So we do have an initial prototype of Pico RV32 going through that process, the same Pico RV32 that was mentioned, I think, by the Juxta Piton folks. We're currently working on automating that process and making it more accessible and more generalizable. You can read more on Yosis, and I believe most of you know about it here already. Some other upcoming features that we have are MIDAS 2. MIDAS is kind of the main engine that drives FireSim and kind of makes that simulators. So that will allow a lot of features that people have been requesting for a while and are kind of still lacking in FireSim, like multi-clock designs. We're adding more debugging and performance analysis features because we understand that that is one of the main pain points when you're doing this, simulators and FPGAs. So we're going to integrate Tracer 5 with a bunch of visualization tools. We're going to add a bunch more out-of-band hardware features. We are also working on having FireSim as a library as part of your design instead of the top level. So today, FireSim is the top level, and you kind of integrate your design inside. We want to allow you FireSim to be kind of a component within a bigger design as well, and integrate it with the full VLSI flow, or as Jerry mentioned, the full Berkeley Agile hardware design ecosystem. We're working on fault injection and more interesting debugging and verification tools, and using FireSim to simulate other distributed systems, not only data centers, but various wireless channels, cars, whatever you want that's distributed. So just to recap, the main point of FireSim, you can kind of see what goes in, what goes out of FireSim. You can build arbitrary RTL and simulate it at kind of an unprecedented scale. Getting to those 1,000 nodes is kind of nice, and run real software on it. And that's really an important point in this context. We automated a whole bunch of things, so it makes using these FPGAs on the cloud very easy. You can deploy the workloads automatically. You can deploy the builds automatically. It's open source. It runs on F1s, and there's no CapEx. And you can evaluate, debug, scale out, basically run through your design and verification process at very high speeds. That's what I have. We'll take any questions.
I think you mentioned synthesizable assertions at one point. Can you describe a little bit more how those might work? Is that something the user has to generate, or are these auto-populated?
So the way this works is it relies on the same sort of, I didn't talk about this in any detail, but the way we build these decoupled simulators is it's this graph, and by applying back pressure on token channels, you can stall local parts of the simulation. And so what we do is to synthesize assertions. You can annotate modules to say, I want all the assertions in this module synthesized, and they'll be wired out to the top of the design and bound to a sort of model, if you will, that's going to consume tokens. And the tokens in this case are a sort of bit vector indicating if any of those assertions have fired. And if they have, that model can then refuse to accept new tokens, thus locally stalling the simulation there. And we can encode this bit vector to point to the right assertion that fired.
Okay.
Yeah.
Thank you.
Hello, I have a question. Maybe you mentioned this already, but in terms of supporting just, like, is there any limitation on the Verilog that you support and don't support in the system?
So that's a good question. So it really depends on which of the two flows you're using. So Alon kind of mentioned the first way is you can build a host decoupled model simply by clock gating some Verilog with something like a clock buffer with an enable, right? So that's how we integrated the NVDLA. For this to work, you have to be able to, the circuit must be clock gateable, right? So if it's multi-clock, that's not going to work. With the Yosys backends, if you can't emit to Fertile correctly, we won't be able to transform it properly. So there's a good chance that if you can emit it from Yosys to Fertile, there's a good chance it'll pass through. But again, like if it's multi-clock, we can't handle that.
By multi-clock, you mean multiple asynchronous clock domains?
Even synchronous clock domains. We only have a single synchronous clock domain in our machines right now. But we're working actively to fix that.
Cool. Right. More questions? No? Okay. I guess that's it. Thanks, guys.
Thanks.
Thank you.